In the last class we have seen that the wave function multiplied by its complex conjugate represents the probability density, and hence the probability of finding the particle inside a finite volume V in space is given by integral psi star psi dV. As wave function changes in time, this probability also changes with time. We are going to study the time evolution of the probability in this class. For that, let's consider the time dependent Schrödinger equation I h cross dou psi by dou t equal to minus h cross square by 2m del square psi plus v psi. From this, we can write dou psi by dou t, an expression for the partial derivative of the wave function, as I h cross by 2m del square psi minus I by h cross v into psi, and taking its complex conjugate results dou psi star by dou t equal to minus I h cross by 2m del square psi star plus I by h cross v into psi star. Multiplying equation 1 by psi star and equation 2 by psi from left side results two equations like these, equation 3 and 4. Adding these two equations, equations 3 and 4, we get this equation psi star dou psi by dou t plus psi dou psi star by dou t equal to I h cross by 2m psi star del square psi minus psi del square psi star. This equation can be rearranged like this one. So the left hand side can be written as the differential of psi star psi, and the right hand side remains the same. Now we integrate both sides of equation 5, and on left hand side of this equation, since the integral is with respect to space coordinates and the differential is with respect to the time coordinate, we can change this integral to something like this. On right hand side, the integral of a differential will give us integrand itself, so it will become simply minus I h cross by 2m psi star del psi minus psi del psi star, and then we apply the limits. One of the admissibility conditions of the wave function is that the wave function and its derivative must go to 0 as r goes to infinity. Hence, applying the limit on the right hand side leads the right hand side to 0. That means we have dou by dou t of integral psi star psi dv equal to 0, or it means that this integral must be, the integral psi star psi must be a constant in time. If we define the quantity I h cross by 2m psi star del psi minus psi del psi star in equation 5 as a vector quantity, probability current density, then equation 5 can be written as dou by dou t of p equal to minus del dot j, where p is given by this probability density psi star psi. So this probability current density actually describes the flow of probability in terms of probability per unit time per unit area. That is, it is the rate of flow of probability density, and this last equation can be rearranged as dou by dou t of p plus del dot j is equal to, this is the equation of continuity for the probability, and it is analogous to the equation of continuity in hydrodynamics and electrodynamics. Integrating this equation over a finite volume leads to this equation: dou by dou t integral p dv equal to minus of closed integral j dot ds, where S is the area of the enclosed volume V. This is the quantum mechanical probability conservation equation. It tells us that the outflow of probability current across a surface causes a decrease in probability in the volume space enclosed by the surface. Or in other words, if the probability of finding the system in some space increases with time, then the probability of finding the system outside that region decreases by the same amount, as this probability increase is caused by an influx of probability current density. Now let's define something called the expectation value. Expectation value of a dynamical variable A is defined by this equation, integral psi star a psi dv. It tells us the value corresponding to the operator A that we expect if we make several measurements on the same wave function, and this is similar to the average value of a measurement in our lab experiments. Usually we take several measurements in lab experiments and then average it out to estimate some value. This is also a kind of statistical average of all possible outcomes of measurements. Here we assume that the wave function is normalized one. If the wave function is not normalized one, then the expectation value is defined as like this, integral psi star a psi dv divided by integral psi star psi dv. So the denominator is basically the normalization factor, and for a normalized wave function this integral psi star psi dv will be 1, so the expectation value will simply become like this. The ordering is very important in this definition. Note that the operator corresponding to the variable which we want to measure has to come in between psi star and psi, and also the psi star should come first and then the operator and then psi, and we should not change the order of appearance of these factors in the expectation value because of some reasons that will be clear when we discuss the postulates of quantum mechanics. In the last class we have seen that the wave function can be written as a product of time independent part and a time dependent part by the separation of variables, something like this. Here this small psi of x is the time independent part of the wave function, and e raised to minus iat by h cross is the time dependent part of the wave function. The probability density is then given by the product of psi star and psi, which can be written like this if you substitute for psi star and psi from this expression. Now you can see that this quantity is constant in time, as there is no time dependent term here. So such states for which the probability density is constant in time is called stationary states. Now let's consider the expectation value of any observable A, which is defined like this, integral minus infinity to plus infinity psi star a psi dx. For stationary state we can write it as like this. If we substitute for psi star and psi in terms of its space and time parts, then the expectation value for the stationary states will become integral minus infinity to plus infinity psi star a psi dx. And here in these wave functions, small, psi star and psi, these are the position dependent part of the original wave functions. And you can see that this time dependent part actually uh, gets eliminated from this expression of the expectation value. So we can see that for the stationary states, the expectation value of an observable is constant in time. As all properties of a quantum mechanical system can be made via expectation values of suitably chosen observables, all observable characteristics of a physical system will not change in time when the system happens to be in a stationary state. The well-known examples for the stationary states in quantum mechanics are the energy levels of isolated atoms, which we will study later. If the particle is in a superposition of stationary state such that psi of xt is given by a linear combination of the stationary state, here Cn is some constant, then the probability density becomes like this. If you substitute for psi star and psi, this can be simplified as modulus psi of xt square equal to sigma n equal to 1 to infinity mod cn square psi n square plus sigma m and n with m not equal to n cm star cn psi m star psi n e raised to I em minus en into t by h cross. So this is just a rearrangement and simplification of this statement. Now this shows that the probability density depends on time if the particle is in a superposition state. So you cannot say that the probability density remains time independent if the particle is in superposed stationary states. Now let's see what is the normalization of a wave function. We have seen in an earlier class that psi of xt, or the modulus square of psi of xt, is the probability density for finding the particle at point x at time t. Since the particle must be found somewhere between x equal to minus infinity and x equal to plus infinity, the wave function must obey a condition integral minus infinity to plus infinity modulus square of psi of xt dx equal to 1, and this is called the normalization condition. Without this, the statistical interpretation would be meaningless, as the probability is a real number between 0 and 1. An outcome of a measurement which has a probability 0 is an impossible outcome, whereas an outcome which has a probability equal to 1 is a certain outcome. Thus, we introduce a multiplication factor n along with the wave function such that n square integral of this quantity must be 1. However, we know that the wave function is a solution of the Schrodinger equation. Therefore, we cannot impose an arbitrary condition on the wave function without checking that the two are consistent. However, if psi of xt is a solution, then n psi of xt is also a solution to the Schrodinger equation, where n is any constant and it can be a complex constant also. So we have to pick an undetermined multiplicative factor n in such a way that the Schrodinger equation is satisfied, and this process is called the normalizing the wave function. And the purpose of this multiplicative factor n is to make the total probability 1. If we try to normalize a free particle wave function e raised to ikx, it becomes impossible to normalize it as the integral diverges. One way to overcome this issue is to restrict the domain of the particle under investigation to an arbitrarily large length L, and then imposing periodic boundary conditions psi of x plus L is equal to psi of x. That means the wave function at this point and at these points or at the boundaries of this box must be having same nature. Now this periodic condition restricts the allowed values of k to only certain discrete values 2 pi n by L, where n is 0 or plus or minus 1 plus or minus 2, etc. So the normalization can now be carried out by integrating the wave function between the limits 0 to L instead of integrating it from minus infinity to plus infinity, and this will lead n equal to 1 by square root of L. Hence the normalized wave function for a free particle can be written as psi of x is equal to 1 by root L e raised to ikx, and this is called the box normalization. In 3 dimensions, the normalization is done in an arbitrarily large but finite cubical box of length L.